In a single replacement reaction, an element is going to replace an element in a compound to form a new element and a compound. In this case, magnesium is a +2, sulfate is a -2, so copper's a +2. The element is trying to get into the compound, so magnesium is trying to replace copper. Since magnesium's plus, it can replace the positive ion. For all of our problems right now, the reaction's going to go. The only way that the reaction won't go is if you have data that's showing that the magnesium and copper 2 sulfate aren't reacting, in which case maybe magnesium can't replace copper. But if given a problem and it says predict the products, then assume that the reaction is going. So copper is going to get kicked out, and then magnesium is going to combine with sulfate. So we get this as our products. For the complete ionic, we're going to break apart anything that was soluble, just like we did previously. Copper is by itself, so that's going to be a solid, and then all sulfates are soluble. Magnesium was not one of the exceptions. So magnesium is a solid, so it doesn't get a charge. That's one of the more common mistakes, is people going to the complete ionic and putting an Mg+2. But elements by itself are going to just be the element. There can't be a charge. Only when it breaks apart, that's when it's going to get charges. So then on the other side, that's a solid, so again it doesn't get a charge, and then our magnesium sulfate breaks apart. Crossing out our spectators. In this case, the only thing that's the exact same on both sides is sulfate, because notice the magnesium on the left doesn't have a charge, and on the right it does have a charge. So bringing down what's left, we get this. We want to make sure that the charge as well as the elements are balanced. We've got a +2 on the left and a +2 on the right. And so we have equal charges on both sides and equal atoms as well. Let's go ahead and try this next one. So chlorine doesn't have a charge right now, but whenever it does make a compound, it makes a -1. So chlorine is trying to kick out bromine, because negative will kick out negative. Bromine gets kicked to the curb, but bromine is diatomic, so it's going to be Br2, and then Na is going to go with Cl. Br2 is a diatomic gas. We can say that it's a gas, we can say that it's a liquid. Regardless, it's going to stay together. And then NaCl is a soluble salt, so that should be aqueous. So for the complete ionic, we get this. We didn't balance the molecular equation, so we can put a 2 there and a 2 here to balance. And again, we could balance our complete, or we can just balance once we get to our net. So looking down at our net ionic, our spectators would just be sodium. And then we need a balance, so we need 2 chlorines and we need 2 bromines. Notice we got a -2 on the left and a -2 on the right, so we have equal charges on both sides and equal atoms. For this next one, you may want to star it. Whenever you have water in a single replacement, we're going to rewrite water as HOH. Lithium is positive, and so it's going to try to kick out that positive hydrogen at the beginning, but it only can kick out the first hydrogen. So hydrogen gets kicked to the curb, and then lithium should be going with hydroxide. Hydrogen's a gas, and then lithium hydroxide is a strong base, so that should be aqueous. So go ahead and do your complete ionic and net ionic. Restart when you're done. For the complete ionic, you should have gotten this. Notice that nothing is crossing out. We don't have any spectator ions because the only thing that dissociated was lithium hydroxide. But I do need to balance that. So I'm going to rewrite it down here and then balance. If I just balanced my elements, I would get this. Notice I have equal lithium. Now I have 4 hydrogens, and 2 oxygens, 2 oxygens. But we've got a +1 and a -2. So this overall left side is a -1, and on the left it's a 0. Those do not equal. So this is not properly balanced. If we had balanced the molecular equation, we would have had a 2 here, a 2 here, and a 2 in front of lithium hydroxide. Had we followed that balancing, we would have had a 2, a 2, a 2, and a 2, which means we need a 2 in front of lithium, and we need a charge in front of, or a 2 in front of lithium ion. Now notice we have a +2 and a -2, which is going to give me a 0, and on the left we also have a 0. So this is the correctly balanced net ionic equation. So make sure again that it's balanced by charges and atoms. And so that would be the benefit of balancing all 3 reactions. You don't have to balance all 3, but you do need to double check that you're balancing the charge and the atoms if you're not balancing all 3. Double replacement reactions, 2 compounds react to form new compounds, so they're swapping partners. One type of double replacement is precipitation, where 2 aqueous solutions react to form a solid. That solid is referred to as a precipitate. The easiest way is to draw a line through the 2 compounds and put their charges. So my positive ion, potassium, is going to go with the negative of the other compound. So outside go together, and then the inside will go together. So K goes with NO3, and copper will go with hydroxide. Copper was a +2, so it's going to keep that +2. Then I can add my state symbols. Potassium nitrate is aqueous because all nitrates are, and that's a weak base, so that is a solid. And then balancing this first one, we needed 2 and a 2 here. So I'm going to pause the video and do the next one on your own. Restart when you're done. So you should have gotten PbCl2 as a solid and NaNO3 aqueous, and then balancing, we needed 2's in front of those. This solid and this solid are our precipitates. Notice we have 2 aqueous solutions forming a solid precipitate. Okay, go ahead and do your molecular equation for this one and then restart. So you should have gotten that. Balancing, you needed a 2 in front of your NaCl. And I haven't mentioned it yet, so you could have also put BaSO4 plus 2 NaCls. So those mean the same thing because you have a plus sign between them. What you cannot write is you could not write ClNa. That would be incorrect. It's got to be positive and then negative. All right, so now let's go and do our complete ionic. Pause the video, do the complete and net, and then restart when you finish those 2. Make sure that your net ionic is balanced. So there's your complete ionic. You could have balanced the complete ionic, but you didn't have to. So then that's your net ionic. Notice that I did the positive and then negative for the reactants. I didn't have to. I could have easily had left it SO4 -2 plus Ba. So both of these mean the exact same thing. You did need to have correct charges, and it did need to be balanced. We can also form a gas directly in a double replacement reaction, but we can also have the decomposition of a product such as carbonic acid. There's 3 compounds that you should be aware of that generally do not exist as products because they're going to start breaking down as soon as they're formed. And that's carbonic acid, sulfuric acid, and ammonium hydroxide. So if you see one of those 3 as products, so again, as a product of a double replacement reaction, we're going to decompose them further as shown here. So carbonic acid breaks down into water and CO2, sulfuric acid to water and SO2, and ammonium hydroxide to water and NH3. Notice they all have water. When you take away the water, you're left with those gases. So for instance, this first one, if we were to predict the products, we would get NaCl and H2SO3. But H2SO3 was one of the ones that we just talked about, so I can draw a line through that one and change that to H2O and SO2. This would be aqueous, this would be a liquid, and this would be a gas. Go ahead and pause the video and try the next one on your own. Restart when you're done. So you got nitric acid. So you got potassium nitrate and carbonic acid. And then that carbonic acid should break down into water, liquid, and CO2 gas. Going to try those last 2 on your own. Restart when you're done. So on C, you should have got an NaCl, aqueous, NH3 gas, and H2O liquid. Notice on this one, I didn't put the NH4OH. I could have written that and crossed it out like I did on the other examples. And this last one also produced ammonium hydroxide, so we get ammonia, water, and strontium sulfide, which is going to be a solid. And then the last type of double replacement is an acid-base reaction. The definition of acid-base reaction is going to be a proton, which is a hydrogen ion, is transferred from the acid to the base. So the acid is going to lose a proton and a base is going to accept that proton. So first, we're going to predict the products just like we did before, so outside, inside. So we get NaCl, that's aqueous, and also HNO2. That starts with H, so it's an acid. That's not one of our strong acids. HNO3 was strong, so this one is going to be a weak acid. I'm going to put liquid just so I know that it should stay together. So for my complete ionic, sodium nitrate should break apart. HCl is a strong acid, so that should break apart. Sodium chloride breaks apart, and nitric acid should stay together, or nitrous acid. Our spectator ions, we have chlorine and sodium. So that's our net ionic equation, and it's balanced. We can really see much easier where the proton went here compared to the molecular equation. If we were just looking at this top equation, it's a little hard to see who gained and lost a hydrogen. But down here at the bottom, we can see that we had a hydrogen, and now HNO2 has that hydrogen attached to it. So this hydrogen must be going over here to combine with HNO2. So the thing that had the hydrogen was HCl, so HCl must be the acid because it lost a proton. And then the base must be NaNO2, or we could say NO2 negative, either of those things, because it gained a proton. So technically we didn't need the sodium, the NO2 is the thing that's gaining the proton. But without the spectators, it's much clearer to see that it's an acid-base reaction. We had a hydrogen combining with a base to make HNO2. Go ahead and do the molecular equation for this one. Restart when you finish the molecular equation. So you should have got an NABR aqueous, and then our other product was ammonium hydroxide, which hopefully you broke down into ammonia gas and water liquid. It is already balanced. So now we just need to do our complete ionic. So go ahead and pause the video and do your complete and net restart when you're done. So that's your net ionic equation. It's balanced by charge as well as elements. One of these is the acid and one's the base. So go ahead and pause the video, figure out who's which, and restart when you're done. You said this one was the acid and this one's the base. You are correct. NH4 is going to lose a hydrogen to OH, and that's how we make H2O over here.